Okay, there you go.
Thanks. Good morning. We're in the middle of composite refractories this week. And on Monday, we went over some background material for corrosion resistance and thermal shock resistance. And we went over all the components uh, of these materials. So today I want to go over these compositions, carbon infiltrated, magnesia, and dolomite. This is more historical. This was started in the 1970s. So this is the first type of composite material from the 1970s. And then the current materials are magnesia carbon for basic oxygen furnaces and ladles. The original carbon infiltrated materials were for basic oxygen furnaces. Alumina silicon carbide carbon. These are used in ladles. Alumina carbon. These are for controlling the flow of molten metals in slide gates and nozzles and shrouds, submerged entry nozzles and ladle shrouds. And then the alumina magnesia carbon, again, is used in ladles. So the composites really started in the 1970s, and the raw materials, the aggregates, dead burned MgO and dolomite, and the binder was simply pitch. So there were two ways of processing these, pitch infiltration of the aggregates before forming, and then pitch infiltration of a fired refractory shape. And these were made with pitch. They have a high carbon yield, usually around 50%, but the use of pitch has declined over the years because when you heat pitch, some of the gases coming off are harmful. They cause cancer. And pitch has a residual carbon content, about 50%. But if you're only using pitch as the carbon source, you don't have a great deal of residual carbon. And that doesn't really significantly improve corrosion resistance or thermal shock resistance. So these materials were processed as follows. You start out with a dead burned MgO or dolomite. That material is crushed and screened into the right particle size distributions for maximum density. And then those powders and aggregates are mixed with the low viscosity pitch. And that's a warm mixing process, maybe 50 to 100 degrees C. And then that material is pressed, and it's a warm pressing operation, maybe 50 to 100 degrees C, to keep the pitch fluid enough. And then once the shape is pressed, it's tempered, maybe between 100 and 600 degrees C. If you're at the higher temperature, you're actually coking the pitch and creating a residual carbon. So that the tempering lasts between 1 and 24 hours. And that is your final product. It goes into storage. And it has to go into cold storage if it's dolomite based. And after tempering at, let's say, 600 degrees C, you pyrolyze the carbon. You'll have 3 to 4% residual carbon in these materials. And then the sintering takes place in the actual furnace. So these were meant for basic oxygen furnaces. They put them in as the lining after tempering. And then when the furnace is up to temperature, the actual sintering of the MgO or dolomite takes place. The other process was an infiltration process. So you start out with the same raw materials, MgO and dolomite. They're crushed and screened as usual to create a particle size distribution that maximizes density. those powders are mixed, pressed, and then those shapes are fired, maybe 16 to 1800 degrees C. And after firing, they're going to have 10 to 20% porosity. So those fire shapes are put in a vacuum, and they're brought up to maybe 200, 250 degrees C. And under vacuum, you introduce the low viscosity pitch that infiltrates the 10 to 20% porosity. So now you have a pitch infiltrated either an MgO or dolomite refractory. So it's already fired. It contains pitch in the pores. And at that point, there's probably 5 to 7% pitch pickup, and that goes into storage. So that pitch is pyrolyzed during the operation in the basic oxygen furnace. So those were the first attempts at making composite refractories. The modern versions I'll go over. The first one is a magnesia carbon composite. It's used in basic oxygen furnaces and ladles. And we'll look at the raw materials, the processing, the microstructure, and then the properties. So magnesia is a primary aggregate. It provides corrosion resistance. So magnesia is a basic refractory. You have basic slags in a basic oxygen furnace. They're high in lime. So magnesia in contact with a basic slag gives excellent corrosion resistance. And you have the sintered version of magnesia or the fused version. And again, the fused version is going to be dense, large crystal size, and it's going to be more corrosion resistant than the sintered version, and it's going to cost more in the fused version. Carbon is usually a natural flake graphite. That provides thermal shock resistance and corrosion resistance. And the binder is going to be a phenolic resin. So these resins wet graphite, they wet the refractory aggregate, so they have good chemical affinity to both graphite and the refractory aggregates. They're after low temperature curing, the resin is quite strong. The carbon content are at least 50%. They could be as high as 70%, so it has high carbon yield. And they're much safer than using a tar or a pitch. So a magnesia source, graphite, and then a phenolic resin as the binder. And then these typically contain one of the following, or maybe one or two of the following: aluminum metal, silicon carbide, and boron carbide. These are the oxygen inhibitors, oxygen oxidation inhibitors. So any of these compounds reduce the oxygen content and the carbon monoxide content. And as I mentioned last time, they do form products that form dense protective oxide or carbon layers. They're basically filling the pores with the reaction products. And that also improves the high temperature strength. So this is a plot of carbon loss versus this antioxidation content. So the carbon loss goes from 0 to 100%. And then the black bar represents a test at 1300 degrees C. The white bar represents a test at 1500 degrees C. So for either of these temperatures, the samples were held for 6 hours in an oxidizing atmosphere. So the first here is at 0%. So there's no additives here. You can see the percent carbon loss is between 80 and 90%. And then you have silicon carbide, aluminum metal, silicon metal, and boron carbide, all at 1%. And then the same for anti-oxidation agents, all at 3%. So as you add these chemicals, you can see the carbon loss goes down. And then as you add a higher level, 3% as opposed to 1%, they go down even more. And actually, B4C, boron carbide, is the most effective here at 3%. It does form a liquid and it wets the material and it forms a good oxidation barrier, but it also lowers the strength because it is a liquid. So all of these different possible additives, they're all somewhat effective in preventing the carbon from oxidizing. And this is a plot of hot strength versus the different types of antioxidation agents. So hot modulus of rupture in megapascals versus temperature in degrees C. The first or bottom graph here is without any additives. So they all show a strength loss because you're pyrolyzing the phenolic resin. But the ones with the additives, you can see the strength starts going up as they react. So the best one here in this case was an aluminum magnesium addition, then an aluminum silicon addition, and then just aluminum. So I'm just trying to show that these additives, when they form their reaction products, whether it be an oxide or a carbide, are going to fill the pores and make the material stronger. So they improve the oxidation resistance, prevent carbon from oxidizing, and they improve the hot strength. So these are uniaxial pressed, and they want to achieve the maximum density. So they're usually a vacuum de-airing process. They can also be isostatically pressed if it's a complex shape. So the properties are really dependent on the green press density. So the higher the density, the lower the porosity, the better the performance of these refractories. So the aggregate is MgO. Again, it's crushed and screened and sized for maximum particle packing, maximum density. Graphite and the antioxidation agents are added. They're mixed with, it's going to be primarily a phenolic resin. Pitch is another possibility, but as I mentioned, it has some hazard. It's a hazardous material, so the phenolic resin is what's basically used today. And then it's pressed under a vacuum to achieve maximum density. It can go through a baking furnace, which is usually less than 200 degrees C. That cures the phenolic resin. It can also go to an optional coking step. So it's heated to greater than 1,000 degrees C to pyrolyze the phenolic resin, forms carbon, and it's an optional step. This coking can also take place in the actual furnace during use, and then these may require machining. So this is a microstructure of an MgO carbon composite. The lighter gray regions are the aggregates, the MgO aggregates. Here's a rather large one. There's another large one, and then there's some medium sizes, and you can see some very small pieces. If you do the chemistry on these aggregates, they're about 97% MgO, and then lime, silica, and iron oxide. You want a high lime to silica ratio, so get rid of the low melting compounds. So this is at 20x. We go to 150x. I guess what I want to also say here, You can see the porosity, and these are a sintered MgO product. So the black regions here are graphite flakes. They're about 98% carbon. So silica and alumina are the impurities, primarily clay material for the impurities. So you can see how the carbon flakes deform during pressing. They conform to the matrix or the aggregates. There's quite a bit of carbon flakes down here at the bottom. This is the matrix region, and I did a chemistry where it's very fine here. So there's carbon from the residual carbon from the phenolic resin. There's some MgO fines, silica, iron oxide, and calcium are the impurities. And we're also picking up aluminum metal, pretty high content in this fine region. So that's your antioxidation agent in this composite. So they're using a sintered MgO, flake graphite, and an aluminum antioxidation agent. And this is another microstructure. These medium gray regions with the black pores, they're the MgO grains. And again, it's a sintered MgO product. If it were a fused material, you wouldn't see this porosity. This light gray regions are all the flake graphites. And again, they kind of deform around the aggregates and the finer matrix during the pressing operation. And the red arrows indicate the pressing direction. So they tend to align somewhat. So they tend to align perpendicular to this horizontal pressing direction. So you can see there's some vertical alignment taking place of the graphite flakes. So when that happens, properties become anisotropic. And here's another microstructure. Here's an MgO particle. Here's some flake graphite. And phosphorite, which is a magnesium silicate, 2-MgO SiO2. A phosphorite has formed. This is after a high temperature. So F here is some phosphorite in this region. So the MgO combined with silica that was present formed some phosphorite, which is a high temperature material. And then silicon carbide may have formed during the firing, reacting silica and carbon, or it may have been an additive. I'm not sure on this micrograph. These are not mine, so I don't know exactly how these were made, but you see graphite, flake graphite, silicon carbide, phosphorite, and MgO. So how these materials wear in service is really a function of the location in the furnace and how the furnace is operated. So the main issues here for wear are dissolution of the magnesia by the slag, oxidation of carbon by iron oxide that's in the slag, oxidation of carbon by ambient gas, oxidation of carbon by the MgO that's actually part of the refractory. There's an erosion when liquid iron flows over the refractory. And then there's also a thermal shock issue, and actually mechanical stresses can also develop. So these are the primary wear mechanisms in the composite material that's used in the basic oxygen furnaces. So for the corrosion of the magnesia by the slag, the dissolution of magnesia, the slag is a basic slag. It's high in lime, so it's lime is present, and then silica is also present. So the slag penetrates the grain boundaries. And when we talked about MgO, we wanted a high lime to silica ratio. But if the ratio is less than 1.86, you can have corrosion starting in the grain boundary regions. We also talked about magnesia being able to tolerate a great deal of FeO, but FeO in the slag also penetrates the crystals, and it can tolerate up to 70 weight percent FeO before it becomes an issue. So to prevent or slow down corrosion of the magnesia by a slag, you want to go to high purity MgO materials, and you want to use the fused magnesia, which is the densest, lowest porosity, and the largest grain size with the fewest amount of grain boundaries. So going simply to a fused material will increase the corrosion resistance. You can also have oxidation of carbon by iron oxide in the slag. So some of the iron that they're converting to steel ends up in the slag. So it's an oxidation by a liquid phase, most of the iron oxide. So the reaction is simply Fe2O3 plus carbon forming CO gas plus liquid Fe. So that is oxidizing the carbon in the composite. So this is wear rate versus Fe2O3 content in the slag. So the wear rate is in millimeters per heat, and then the Fe2O3 content is in weight percent up to 25. So the tap hole location in a basic oxygen furnace, the trunnion locations, the trunnions are the pivots on the side of the vessel for tilting the vessel for removing the steel or the slag. And then also here's an application at a ladle slag line. But you can see in all these cases, as the Fe2O3 content in the slag increases, the wear rate increases. You can also have oxidation of carbon by ambient gases, and that's mostly due to oxygen or carbon dioxide. So I went over these a little bit on Monday, but I show them again. Carbon plus oxygen forms carbon monoxide. That takes place at temperatures less than 1,000 degrees C. And then above 1,000 degrees C, carbon plus oxygen forms CO2. And then the CO2 can react with carbon to form more CO. So one of the things that is done in a basic oxygen furnace is something known as slag shielding. So after you remove the steel, the slag that's left, you rotate the furnace, kind of rock the furnace, and splash the slag on top of the refractory. So you're putting a slag layer at the hot face of the refractory, and that slag layer is a diffusion barrier to oxygen or CO2 and slows down the oxidation. The slag layer is very important for really improving the life of these refractories. So the effect of shielding by the slag layer, we look at the decarbonization depth, the depth where carbon is removed, that's in millimeters from 0 to 20 versus the temperature. So these are experiments where there was a plain MgO carbon composite versus a composite that had a slag coating. These samples were heated for 10 hours at these different temperatures. So the plain material, you can see how the decarbonization depth increases as the temperature increases. But when you put a slag coating down, um, as the temperature increases, the carbon depth that's decarburized decreases. So that the slag becomes more efficient as the temperature goes up. It, it, it coats the refractory hot face. And so here it's probably not very fluid, becomes somewhat more fluid and does a better job of coating and better job of preventing decarburization. So you can see the big difference between having a slag layer on a refractory hot face versus no slag layer. So this is an operating parameter that's important for extending the life of these materials. So this is an MgO aggregate in a carbon matrix. So the carbon can actually be oxidized by the refractory itself, by the MgO. So direct oxidation of a metal oxide. So MgO plus carbon forms Mg gas plus CO gas. So this reaction takes place at high temperatures right at the hot face. It has to be a fairly high temperature to have this reaction go to the right and remove oxygen from the magnesia. So right at the hot face, this reaction takes place. The Mg gas diffuses to the hot face, and then it reacts with the ambient atmosphere, which contains oxygen. So it goes backwards. It forms the Mg gas reacts with oxygen to form MgO again. So this is a refractory microstructure at the hot face. So right here is the hot face. This micron marker is 200 microns. So back about 200 microns, right behind the hot face, you're forming a dense MgO layer. So this bright area is the MgO layer that forms. So you really don't want to destroy your MgO by having a reaction with carbon, but this turned out to be an advantage here because this Mg gas diffuses to the hot phase, reacts with oxygen, forms a dense MgO layer, which is another protective layer preventing the decarbonization. This is the kind of thing that's not planned when you design a refractory. People discovered it happened when they examined used refractories from these vessels. And then there's also direct wear by liquid iron. So you have high abrasion when the iron or steel and the slag move together, and you don't have a stable slag layer at the hot face. And when you have this combination of metal and slag flowing, that removes the carbon and magnesia at a higher rate. So in order to prevent this, you want to make the densest structure possible. The carbon is the softest material, soft relative to the MgO, so it's going to abrade or wear faster. So you want a dense structure, a low carbon content. You want these metal additions because they improve the strength and they reduce the abrasion. So the denser the structure, the lower the carbon content. The addition of metals all increase the high temperature strength, and that improves the abrasion resistance. But doing this, making it denser, lowering the carbon, increasing the strength, that's going to reduce the thermal shock resistance. So there's always a trade-off on how these materials are made. So this is abrasion index versus hot modulus of rupture. And this goes from 0.4 to 2. So the higher the index, the higher the abrasion. And then the hot MOR is in kilograms per square centimeter. And the hot modulus was measured at 1400 degrees C. And in this experiment, a refractory finger or bar is lowered into molten material at these temperatures, 1650 to about 1700 degrees C. and that bar is rotated. In this case, it was 100 RPMs, revolutions per minute. So you can see as the hot strength is improved, the abrasion goes down. So the stronger the material, the lower the abrasion. And that has to be hot strength, not room temperature strength. And then thermal and mechanical spalling, reduce cracking with increasing graphite content and increase cracking with increasing aluminum metal content. So this is an index. Index B is proportional to the number of cracks. So the higher the index, the higher the crack density. Also the higher crack density reflects more thermal shock damage. So this is basically thermal shock damage versus graphite content, thermal shock damage versus this anti-oxidation metal aluminum. So the graphite content goes from 10 to maybe 30%. And these materials were thermally shocked either by water quenching or air quenching. So in water quenching, a refractory sample is dropped into water. That's very severe, as opposed to air quenching, which is just taking it out of a hot furnace and letting it cool in air. So here's the thermal shock damage for air cooling and then for water cooling. So the damage goes down with increasing graphite content. So reduce thermal shock damage with increasing graphite content, but increasing thermal shock damage when you add these antioxidation materials. So this is aluminum content from 0 to 5%. Water quenching, the black circles, and air quenching, the open circles. So there's a slight increase in thermal shock damage as you add these antioxidation agents because they are actually decreasing porosity and increasing strength, which is going to lower the thermal shock resistance. So a couple key properties. This is a sintered MgO material. This is a fused MgO. And then this is a combination of a 50-50% combination of sintered and fused MgO. The carbon contents on the sintered MgOs start at 7, go up to 30, and these other two are at 18. So the density is going to decrease with increasing carbon content from about 3 to about 2.7, and that's in grams per cubic centimeter. You try to make these, you try to press these at the lowest possible porosity. These are all around 4%. These are bonded with a phenolic resin. So the cold crushing strengths are rather good because they're very dense, low porosity. The resin is pretty strong after curing. So they're all around maybe between 4 and 9,000 PSI. And the hot MOR is also rather good. This is at 1400 degrees C. Maybe 1300 to almost 2600 PSI. These are obviously done in a reducing atmosphere. So these are some typical properties and carbon contents for these types of materials. The alumina, silicon carbide, carbon composites are used in ladles. And we'll look at the raw materials, how these are made, and some of the properties. So the alumina is added because it has good corrosion resistance. The neutral refractory has got good corrosion resistance in either acidic or basic slags. The sources of alumina are fused alumina, sintered. We also can use bauxite and andalusite. The carbon is there for thermal shock resistance and corrosion resistance. And silicon carbide can be an antioxidation agent, but it can also be a significant additive. It not only protects carbon from oxidizing, but it is material that's corrosion resistant. And the binder is again going to be the phenolic resin. These are either uniaxially pressed or isostatic pressed. And again, maximum density is desired, so they're pressed under a vacuum. And again, they're trying to achieve high density, low porosity to give the best performance of these materials. So you start out with alumina and silicon carbide. And again, we're crushing these materials, screening them into the right size distribution for optimum packing. Graphite and antioxidants are added during the mixing, and then the phenolic resin is also added. They're pressed under vacuum, and they're baked just like for the MgO carbon composites to set the resin. So they go through a baking furnace at maybe 200 degrees C. And the optional step is to coke it at temperatures greater than 1,000 degrees C. This would be done in an atmosphere that doesn't contain oxygen. And then they may or may not be machined. So the thermal shock resistance of these materials is good. They're a little bit better in thermal shock than the magnesia carbon refractories because alumina and silicon carbide have lower thermal expansion coefficients than magnesia. So the lower thermal expansion prevents thermal stresses to a better extent. So that gives rise to better thermal shock resistance. And alumina and silicon carbide have good corrosion resistance along with the carbon. So these are used in ladles. So there's some treating that takes place in the ladles, and different agents are added. FeO is added to remove silicon, CaO, CaF2, CaC2, and Na2O are added to remove sulfur and phosphorus from the steel. So you want to use a fused alumina for maximum corrosion resistance. It has the larger crystals, minimizes the amount of grain boundaries. So fused alumina is better than sintered alumina. It has better resistance to some of these additives like FeO, Na2O, and CaF2. FeO and Na2O can also oxidize the silicon carbide. It forms silica, SiO2, and carbon. So those are some of the reactions that can take place. So if you plot the degree of wear from 0 to 6, 6 being the highest wear, for different materials in contact with different slags. So this is a high alumina material, and then we have an alumina silicon carbide carbon composite, and the second one, slightly different compositions. So the black bar is a slag that removes phosphorus. The bar with the dots is a slag that removes silicon. And the white bar is a slag that removes sulfur. And the crosshatched bar is a basic blast furnace slag. And these are the test temperatures. So you can see the wear in all cases decreases for the composites relative to just a high alumina refractory. So you can see how effective they are in decreasing the wear rates. So they can be used in torpedo ladles or hot metal ladles, which is basically a large crucible. And there's different positions in these ladles. So these are zones. So there's different refractory compositions in different locations. So this is a slag line location. This is location that's in contact with the iron. And this may be the sealing of the torpedo ladle. And in the hot metal ladles, you have a slag line. And then where you're in contact with hot metal, maybe at the top near the slag line or at the bottom of the ladle. But different refractories are put in different locations uh, depending on the wear rates. All the different locations have different wear rates. So you put your best refractories where you have the highest wear rates. So the density is a function of the composition. And these are all between 5 and 10% porosity. And at these lower porosities, the cold crushing strength in PSI is quite high, 5 to maybe close to 8,000 PSI, and the MORs are also rather good. These are also cold MORs, all around 2 to 3,000 PSI. And then these are how the compositions are changed for the different locations. So you have your alumina contents are quite high, maybe 50 to 80%. Your silicon carbide is maybe 5 to 8%. Carbon is around 10 to 15%. And they've added here, which I didn't mention, SiO2. That's a fused silica. That has really low thermal expansion. So this is added to provide thermal shock resistance. So it's only 1% here, 9 and 7. And then these go quite a bit higher, all the way from about 9 to 30% fused silica. So the fused silica is an addition to improve the thermal shock resistance. The aluminum carbon composites are used in slide gates and tubes. So the slide gate plates, tubes like a nozzle, a submerged entry nozzle, and a ladle shroud. So these are plates and tubes, and we'll look at raw materials, processing, microstructure, and properties. So alumina is the primary aggregate. It provides corrosion resistance. It could be either sintered or fused. Sometimes zirconia or zircon is added for corrosion resistance. Sometimes mullite is added. And if you remember, mullite has a pretty low thermal expansion, so it's added for thermal shock resistance. We've also talked about clay additions. The clay, when it's sintered, protects the graphite from oxidation. And the carbon in these could be a flake graphite. It could be an amorphous carbon. It could even be carbon black. So the alumina carbon composites could have multiple other components. And of course, you have to have the metal antioxidation agents, silicon, aluminum, and magnesium. Also, sometimes silicon carbide and boron carbide are added, and the binder is always going to be a phenolic resin. So to make a plate, you have your fine powders, your medium and coarser aggregates. They are pre-mixed, and then you add your binder, which is your phenolic resin, and they're mixed, and they're basically kneaded together to form a mass, and that mass is then crushed, and those crushed particles are then pressed during the forming operation. The material is dried, it's fired, and it has to be fired in a non-oxidizing atmosphere. And depending on how they're firing it, or whether they're just coking the resin or doing actual sintering, the firing temperature can be between 400 and 1400 degrees C. So after firing, it becomes somewhat porous again because you pyrolyze the resin. You create some more porosity. So you can infiltrate more resin after firing to fill the pores. And then the material can be machined and you have your final product. For the tubes, you start out again with your fine powders and your medium and coarse powders. They're mixed, and then your binder, which is your phenolic resin, is added, and this goes through a kneading operation. So now you have a mass that's crushed or granulated. And the forming process is by cold isostatic pressing. The material is dried after pressing, fired under a non-oxidizing atmosphere. If machining is necessary, there's a machining step. Sometimes these materials are coated with a glaze or a glass. That's an oxidation barrier to prevent oxidation of the carbon. And then you have your final product. So for the nozzles, this is just a little more detail on the processing. So you have your material that's mixed and granulated, and that material goes into these filling stations. And then the filling stations drop the material into these flexible bags that have this metal mandrel down the center. So there's a metal mandrel, and the flexible bag surrounds that. And then there's a space here, which is filled with these crushed aggregates or granular material. So once this is filled, pressure is applied either by water or air, and that forms the tube around this metal mandrel. So you remove the mandrel in the bag, and you end up with these tubes. This one just shows tubes with a top on it from the way it's processed. Obviously, that has to be removed for the application. So these tubes go through a curing furnace. So this just sets this is low temperature, it sets the polymer, cures the polymer. And then it can go through a glazing operation, like I just mentioned. So you spray on a glazed powder, coats these tubes. And if you do that, you can go down here to what's known as an open firing. So it can be fired in the air atmosphere because that powder will melt, form a glaze or a glass, and coat these tubes, and that prevents oxidation. If you don't coat them, you have to do what's known as a closed firing. That would be in an inert atmosphere, nitrogen or argon. So that prevents oxidation of the carbon. So the tubes and the slide gates are used like this. This is the bottom of a ladle. Right here is a slide gate. So the slide gate is just two plates. Each plate has a hole in it. When you align the holes, the metal flows. When the holes aren't aligned, you stop the metal flow. So here's the bottom of a ladle with a slide gate, and then here's a ladle shroud, a tube that sends the metal to this other vessel known as a tundish. So now you have steel in a tundish, and this one, instead of a slide gate here, which is probably more common, this one is showing a stopper. So you push the stopper down, you stop the flow of metal, you pull it upward, you allow metal to flow. By positioning that stopper, you can control the metal flow, and this is a continuous casting mold. So here's another tube. This is the submerged entry nozzle. So here's your ladle plates and various tubes are used for controlling the flow of molten metal. The microstructure looks like this. The darker gray particles labeled A are alumina, and you can see there's no porosity here. So this is a fused alumina, it's very dense. These light gray regions are the graphite flakes. They're quite easy to see. The bright metal, these bright spots are silicon metal. So you can see where the antioxidation agents are added. And then the residual carbon from the resin are these darker black regions that are around the fused alumina aggregate and sort of around the carbon aggregates and in the matrix. So the compositions are designed to optimize both corrosion resistance and thermal shock resistance. So on the left-hand side here in the vertical axis, we have low to high corrosion resistance. On the right-hand side, we have low to high thermal shock resistance. So the carbon here goes from 0 to 60%, and the alumina aggregate goes from 100 down to 40%. So they all add up to 100%. So increasing carbon content to the right, increasing alumina content to the left. So the higher the alumina content, the higher the corrosion resistance, the higher the carbon content, the higher the thermal shock resistance. So this plot with the arrow pointing to the right is corrosion resistance as a function of composition. And then this plot pointing to the right is thermal shock resistance as a function of this chemistry. So right in the middle, you're optimizing both the thermal shock resistance and the corrosion resistance. So this region is where you have your optimum performance. On these materials, they also measured RST. We talked about R4 prime and RST. RST is for a material with large cracks. It's actually in degrees C square root of meters. So as you remember, the higher the R parameters, the higher the R4 prime, the higher the RST, the better the thermal shock resistance. And this is the percent graphite. So as you increase the graphite content, you increase RST, and that means you're going to have better thermal shock resistance. And here's just another plot, very similar, low to high corrosion resistance on the left, low to high thermal shock resistance on the right. We have our carbon content. In this case, it's fixed at 30 weight%. And then the alumina content starts at 70, drops down to 20. And now they're adding some fused silica, the low expansion material from 0 to 50%. And that's added to improve thermal shock resistance. So this plot is the, with the arrow pointing to the left is for corrosion resistance. This plot with the arrow pointing to the right is for thermal shock resistance. So the corrosion resistance drops as we decrease the alumina content, and the thermal shock resistance increases as we increase the fused silica content. So again, if you want to optimize the performance, you have to use compositions in the center of this diagram. I thought I'd mention this slide for glaze protection. So the vertical axis is efficiency in providing oxidation resistance, and then the horizontal axis is temperature. So there's a temperature region for maximum protection against oxidation. So if you're down here at a low temperature, you spray a powder onto the surface of the composite. If the temperature is too low, that really doesn't soften and melt and flow. It doesn't provide protection. If the temperature is too high, the glaze becomes very fluid and it just flows off of the composite. But somewhere in the middle, there's a temperature range that gives just the right viscosity to coat the composite material and provide the best oxidation resistance. So if you're putting a protective coating, you have to be aware of the viscosity temperature relationship so that you put the best coating on the composite for the most efficient blocking of oxidation. So for the plates, these are ladles that might be, well, the plates might be used in either a ladle or a tundish. Here's a ladle tundish application, and here's just a ladle application. So they have a certain size hole. These are the hole sizes in millimeters. The bulk densities are going to depend on the composition, but you want the lowest porosity possible. So low porosity resin bonded materials are going to have good cold crushing strength. These are all around 30 to 35, 36,000 PSI. Because it's alumina, it's going to have pretty high thermal expansion. This is at 1500 degrees C in percent. And then these are the compositions. So you have alumina and carbon. Alumina is a primary aggregate, and carbon may be up to 12, 15%. And these materials are adding some fused silica, a 0 to 3, and maybe 1 to 6%. And they're also adding some zirconia for corrosion resistance, maybe up to 12%. So depending on the chemistry, you're going to have low, medium, or high thermal shock resistance, or high, medium, and low corrosion resistance. So the composition in the middle here optimizes both thermal shock resistance and corrosion resistance. So the higher the alumina content, that generally gives the highest corrosion resistance. The higher the carbon content, that tends to give high thermal shock resistance. And then the different tubes, there's 3 different compositions here. These are the bulk densities, which again is going to be a function of the composition. These are a little more porous. The porosity is there to provide thermal shock resistance. You can imagine a cold tube, and all of a sudden you have hot metal flowing through it, very severe thermal shock conditions. The cold MOR is quite good, over 2000 PSI. And the thermal expansion here is at 1000 degrees C. It has a high silicon carbide and carbon content. Even though it's an alumina aggregate, these contents are pretty high in these materials. So the thermal expansion is quite a bit lower because of the high carbon and silicon carbide contents. Again, there's a trade-off between thermal shock and corrosion resistance. So alumina is the primary component. Carbon and silicon carbide contents are quite high. The fused silica is again added to lower the thermal expansion. That's probably one of the reasons why these are pretty low. And zirconia is added for corrosion resistance. So the higher the silica content, the higher the carbon content, the higher the thermal shock resistance. And then the higher alumina contents are going to give higher corrosion resistance. And then this is your compromise in the middle, where you have both decent thermal shock resistance and decent corrosion resistance. And this should be the last material, aluminum, magnesia, carbon. These are used in ladles, and we'll just look at raw materials, processing, and properties. So alumina is added for corrosion resistance. It could be a sintered alumina, fused alumina, or it could be from bauxites. Magnesia is also added for corrosion resistance. It could be sintered or fused. So what happens is when you start out with aluminum and magnesia, you're going to end up with spinel. And the spinel is also going to provide corrosion resistance. You can actually add spinel, but there's some advantages of adding aluminum and magnesia and forming spinel in situ in the furnace during the application. The carbon source is going to be natural flake graphite, amorphous carbon, or even carbon black. Your antioxidants are going to be silicon metal, aluminum metal, or some type of magnesium alloy. And the binder again is the phenolic resin. So you start out with alumina and MgO raw materials. Again, we're crushing and screening to get the right particle size distribution so that when we press the material, it'll have maximum density. You're adding graphite and antioxidants during mixing, plus the phenolic resin. These are vacuum de-aired during pressing, and they're just going through a baking furnace to cure the phenolic resin. So it's a low temperature furnace. So what happens during the use is that spinel forms. So when spinel forms, it's a lower density material, so it's going to provide residual thermal expansion. So this is an irreversible thermal expansion because you form spinel. So the reaction is MgO plus alumina forming MgAl2O4, which is spinel. So the product expands, and when you're lining a ladle, that closes open joints. And also this expansion reduces the open porosity. Spinel has pretty good thermal shock resistance and pretty good corrosion resistance. So the spinel, when it forms, provides this irreversible thermal expansion behavior or residual thermal expansion. So this is thermal expansion after 1600 degrees C as a function of MgO content. And this is a wear index as a function of MgO content. So you can see the residual expansion goes from about 0.5 to 3% as you increase the MgO content. And these are for samples, again, fired at 1600 degrees C, a high enough temperature to form the spinel. And so the more spinel you form, the wear rate goes down. So the wear index decreases. So the spinel formation decreases the wear rate. So these are some possible compositions. You can see the alumina contents on these first two are in the 80% range, and then in these other two are in the 60% range. So then you have a small amount of MgO for these first two high alumina contents, but you'll have more MgO when the content drops down to around 65%. These carbon contents aren't the highest. They're range from 2 to maybe 10%. And then there's some few silica additions to enhance the thermal shock resistance. So bulk density is really a function of composition. The higher the carbon content, this one has the highest carbon content, it's going to have the lowest bulk density. You want low porosities. So these are all under 8%. Your cold crushing strengths are going to be high on a resin bonded low porosity material. And the hot MOR, these are at 1500 degrees C. That's a pretty high temperature. These are all pretty good. Even 600 is a pretty good hot MOR at 1500 degrees C. These have to be measured in an inert atmosphere. And then the thermal expansion, because of the alumina and MgO present, the thermal expansion at 1400 degrees C is going to be quite high, well over 1%. These are a little bit higher because of the higher MgO content. This is almost 1.7. But the permanent linear change, the irreversible thermal expansion after 1500 degrees C, they're all positive. So this is maybe 0.5%, 0.25%. This is greater than 1%. This is about 0.75%. So these are a little bit higher because you have a higher MgO content. It's going to form more spinel in this material and these two materials than these two. So that's what I have on different composite materials. Again, if you ever have any questions, you can always email me or even call me. So next lecture, we're gonna have one lecture on insulating materials, and then we're gonna have a couple lectures on the monolithic materials. So have a good weekend, and I'll see you on Monday. Thanks again.